fuel cells provide electrical power for spacecraft instrumentation. This is the concern of another division of engineering and development of the Manned Spacecraft Center, the Instrumentation and Electronic Systems Division. Instrumentation is the means for providing all necessary intelligence about spacecraft performance and environment to the pilot and to monitors on the ground. It includes cameras, tape recorders, radiation detectors, heat sensors, special instrument panel displays, and other monitoring devices. Electronic systems are used for communication, tracking, and data handling on board the spacecraft. One of the major functions of the Instrumentation and Electronic Systems Division is to provide all instrumentation and communication systems for the early Apollo research and development modules called boilerplates. This includes purchase of off-the-shelf items where possible, or the development of special equipment where necessary, evaluation of equipment, complete test and flight qualification of components, assembly of test breadboards, final system checkouts, and shipment to the contractor for installation on boilerplates. Close quality control of all instrumentation and electronic systems is maintained by the division through extensive development, modification, and testing. First, in the standards and quality assurance laboratories, the test equipment itself is calibrated to meet Bureau of Standards values such as pressure, frequency, direct current voltage, and electrical resistance. The test equipment then calibrates flight gear and is used in acceptance and qualification testing of systems and components. In the environmental testing lab, equipment includes oxygen chambers, vibration equipment for shake tests, a small centrifuge capable of testing a 100-pound item to 100 Gs, a shock tester, humidity and high temperature ovens, and vacuum chambers which can closely simulate the vacuum of outer space. In the instrumentation laboratory, instruments are also modified and prepared for field tests. Several tests are made in the qualification processing of instruments. These pictures show tests on a high-speed camera like the cameras placed on launch vehicles for recording events such as this Air Force photography of the separation of stages on a Titan vehicle. Here, a battery pack is being cycled to determine an optimum charge rate. Heat sensors under development for Apollo heat shield instrumentation are subjected to acetylene flame tests. The heat sensing element generates an electrical signal proportionate to the heat surrounding it. The tests are a good example of how electronic instrumentation is used to gather data for spacecraft systems design. Wave analysis is another useful technology for spacecraft systems design. This spectral wave analyzer can take complex waveforms such as those recorded in vibration tests and break them down into frequency components and amplitudes which can be converted to equations of use to the structural design and test engineer. The first facility of the Instrumentation and Electronic Systems Division in operation at the Clear Lake site of the Manned Spacecraft Center was a nuclear radiation laboratory. Here, the effect of radiation on instruments and systems can be studied. Critical units which may be affected by radiation in spaceflight are electronic components such as transistors and diodes, and also photographic materials such as film and camera lenses. In addition to space radiation, the use of nuclear power systems for future missions, such as those to the planet Mars, will create high radiation levels on systems and components within the power system itself. To simulate these radiation levels, the radiation laboratory has been equipped with a variety of nuclear sources and generators. One such system is the so-called gamma irradiator containing radioactive cobalt-60. Test specimens can be placed in the irradiator and subjected to gamma dose rates as high as 20,000 roentgens per hour. Some components, such as optical lenses, which might be part of a closed-circuit television system used to monitor power systems operations, show significant changes under such smaller doses of radiation. 5,000 roentgens will discolor or blacken some camera lenses. Photographic film is also given irradiation tests, as well as other tests such as those which reveal the effect on film of space vacuum. Scientists and engineers of the division also study and test communication equipment and methods. In their work, they utilize several facilities, from this shielded room used to isolate radio frequency sources and to test instruments for sensitivity to radio frequency interference, to this microwave and optical laboratory. In this lab, experiments are being conducted with lasers, so called from the initials of the phrase, light amplification by stimulated emission of radiation. Many materials can be energized in this manner. This is a pulsed laser using a ruby for the conversion of electrical energy into the radiant energy of an intense beam of light in pulses measured in thousandths of a second. And this is a gas laser using helium and neon for continuous rather than pulsed emission. A single laser beam has the theoretical capability of transmitting a vast amount of communication data. This laser uses gallium arsenide, which produces a comparatively broad bandwidth. A laser radar may possibly be developed for such uses as rendezvous and docking of Apollo spacecraft. Such devices for the maneuvering of spacecraft will be utilized by another division of engineering and development, the Guidance and Control Division. To obtain data for all areas of guidance and control, the division's flight simulation branch uses both digital and analog computers to take the place of spacecraft not yet built. By simulating various conditions of spaceflight on a computer, a great deal of time can be saved and the cost of building experimental hardware is eliminated. In a simulated flight problem, an engineer performs the functions of the pilot. The computer takes the place of the free-flying spacecraft, whose inertia and reaction control characteristics are programmed in the computer. After a run begins, the computer computes the motions and new attitudes of the simulated spacecraft and places these on the pilot's flight instruments. A model of the spacecraft, in this case Apollo's Lunar Excursion Module, may also be used to represent the movements of the spacecraft on a plot board. With hand controls, the pilot fires jet thrusters and controls the main engine of the simulated spacecraft. He can cause the craft to roll, pitch, and yaw, or to move in different directions at different speeds. The blip on the scope shows the pilot his position with respect to his destination. This device, which space technologists call an 8-ball, is an attitude indicator. It tells the pilot the attitude of his spacecraft. By simulation, problems in any phase of spaceflight can be extensively studied. This table is another simulated spacecraft. Called an air-bearing table, it is mounted on air in a manner which makes possible an almost frictionless environment. It is used by the Guidance and Control Division to study the accuracy and flight characteristics of guidance systems. In the study underway here, the pilot, a control and guidance engineer, is testing the torquing capability of a two-axis gyro to move the spacecraft clockwise and counterclockwise. The gyro is operated by the engineer pilot electrically through tie lines from the torque reaction box. Due to its almost frictionless mounting, the table can continue to rotate for more than 24 hours after being set in motion. Thus, the table simulates closely the frictionless condition of flight in space. Other tools used by the Guidance and Control Division include this linear rate table to measure the accuracy of accelerometers, this oscillating rate table which can test almost any accelerometer to tell how well it operates, standard tools such as this square wave generator being used to verify a simple switching logic circuit, and more advanced testing devices such as the optical divider, here being aligned prior to its use in checking optical guidance instruments for accuracy. A fifth division of engineering and development determines the need and helps design special test facilities required in support of the Manned Spacecraft Center's program. This is the Structures and Mechanics Division. The Space Simulation Laboratory at the permanent Clear Lake site is an example of such test facilities. This is a 1/60th scale model of the laboratory designed to house 2 chambers containing vacuum and nitrogen refrigeration systems and solar simulators to simulate the environment of space. The chambers will reproduce temperature and vacuum conditions to be encountered on journeys to the moon and beyond. The interior of the small chamber is 25 feet in diameter and 30 feet high. The large one is 55 feet in diameter and 95 feet high, containing a giant's handful of outer space captured on Earth for tests of complete Apollo spacecraft modules. In such a simulated space environment, the Earth's gravity, of course, cannot be changed, but the vacuum which can be created in each chamber is close enough to the hard vacuum of space for an ordinary light bulb filament to continue to burn without its glass covering. The first facility of the Structures and Mechanics Division to go into operation at Clear Lake was this arc jet used for testing spacecraft heat shield materials. The arc jet produces a stream of high-temperature air with energy similar to that associated with entry into the atmosphere at superorbital velocity. Air is heated in the arc jet by passing nitrogen through an electrical arc and mixing oxygen to simulate the chemical composition of air. The air is heated to temperatures in excess of 8,000 degrees Kelvin with heat content of over 15,000 BTUs per pound. At such temperatures, the arc heater itself must be water-cooled to maintain its structural integrity. A test is monitored by motion picture and television cameras, as well as thermocouples in the arc jet system. Test runs are programmed manually. Test control consoles display flow rates and other operating parameters. Samples of heat shield materials are placed in the arc jet by a specimen inserter, which can also remove a sample at a specified time. Post-test analyses are made of each sample. Whether the spacecraft structure be part of a heat shield or a new type of astronaut couch, it is tested by engineers and technicians of the Structures and Mechanics Division. In this qualification test, proving a crew system's design concept, accelerometers are used to measure the vibration response of both couch and dummy pilot to determine how much vibration energy can be absorbed by a net couch during liftoff and re-entry. The structural characteristics of recovery systems are also analyzed by structures and mechanics engineers. The returning space traveler must be equipped with adequate survival gear in the event of landings in remote areas on land or water. Survival equipment is one of the responsibilities of the Crew Systems Division. Various contingencies are studied, such as water filling the pressure suit and difficulties both before and after the astronaut slips out of his parachute harness. These underwater scenes show life rafts and garments being given flotation tests to determine the best designs for keeping men afloat in the proper position. The aim is to develop a single piece of flotation gear which will keep survivors in a semi-supine position under all circumstances. A 3-man life raft is being developed for Apollo survival. Flotation characteristics of new configurations